The night sky presents a perfect picture of eternal constancy, but this is an illusion. Stars, the very anchors of the cosmos, can simply vanish without any explanation. This is the core of a profound astronomical mystery centered on 26 specific stars that disappeared from photographic plates, leaving behind not just empty space, but one of science's greatest puzzles, the missing mass problem. If stars can be erased so completely, what does that say about the laws we believe govern the universe itself? By the end of this exploration, you will understand the full scope of this cosmic detective story, from the first baffling discovery to the revolutionary theories that attempt to explain it. We will journey from dusty observatory archives to the cutting edge of theoretical physics, confronting the possibility of failed supernovas, alien megastructures, and even new forms of matter. How stable do you believe the universe around us truly is? This cosmic detective story began not with a flash, but with the slow, deliberate work of routine. For decades, starting in the middle of the 20th century, astronomers were conducting a grand celestial census. Their tools were not digital sensors but large glass photographic plates coated with a light-sensitive emulsion. Observatories like the famed Palomar in California would systematically photograph the entire night sky, section by section, creating a detailed frozen record of the heavens at a specific moment in time. The true power of this method, however, lay in the comparison. Years later, astronomers would take another photograph of the exact same patch of sky. They would then place the old plate and the new plate side by side in a device called a blink comparator. By flipping rapidly between the two images, any object that had changed in brightness or position would appear to jump out. It was a painstaking, eye-straining process, relying on the sharp focus of a human observer to spot the subtle dances of variable stars or the slow drift of asteroids. This was the established, methodical rhythm of astronomical discovery, but within this rhythm, buried in the vast archives of these sky surveys, waited a profound anomaly. The census was about to report that some of its citizens were missing. The rhythmic click of the blink comparator was the only sound in the dim room, a steady metronome marking the passage of celestial time. An astronomer's eyes, trained for subtle shifts, scanned the two glass plates as they flickered back and forth. Star, 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 asteroid, star. The pattern was hypnotic, a predictable dance of light. Then the rhythm broke. On the older plate, a faint but distinct pinprick of light held its place. On the newer plate, taken years later from the same observatory with the same telescope, there was only empty blackness. The star had not dimmed, it had not moved, it was simply gone. The immediate assumption was not of a cosmic mystery but of a mundane error. Perhaps a flaw in the photographic emulsion had created a false star on the first plate. Maybe a random cosmic ray, a high-energy particle from deep space, had struck the new plate exactly where the star should have been, leaving a tiny blemish that mimicked its absence. The first step was always to eliminate the obvious. They checked the logbooks for cataloging mistakes. They inspected the plates under magnification for physical scratches or defects. They searched other sky surveys from the same era, yet the evidence held firm. The star had been there, documented and catalogued, and now it was not. This was no plate defect. It was an absence, a true negative exposed by the relentless process of comparison. The search for a reasonable explanation had just begun, and the first, simplest answers were falling away, leaving behind a growing sense of unease. What began as a single anomalous case soon multiplied into a pattern. As astronomers widened their search, meticulously comparing plates from different sky surveys spanning decades, they uncovered more of these ghost stars. One by one, they were catalogued, each disappearance a silent alarm. The initial bafflement gave way to a focused investigation, a systematic hunt through the archives of light. The result was not just a handful of curiosities, but a definitive list of 26 stellar objects that had unequivocally vanished. These were not the faint, distant stars at the edge of detection, where a simple equipment glitch might be blamed. These were relatively bright objects with an apparent magnitude around 13, which in astronomical terms means they were clearly visible and well within the detection capabilities of the telescopes and plates of their time. They had been firmly present in photographs taken before the year 1950 and were absolutely absent in images taken after 1950. This was not a gradual dimming, a slow fade into obscurity. This was a binary switch from on to off. The creation of this list transformed the mystery. A few oddities could be dismissed as freaks or errors, but 26 identical cases points to a phenomenon. The pattern itself became the central clue, demanding an explanation that could account for not one, but 24 stars stepping out of the universe without a trace. Astronomers are by nature a skeptical bunch. When faced with the impossible, their first instinct is not to leap to the extraordinary, but to meticulously dismantle the ordinary. The 26 vanishing stars presented a challenge that demanded this rigorous process of elimination. Every conceivable, mundane explanation had to be tested and discarded before any truly cosmic theories could be entertained. The investigation began close to home with the tools and the atmosphere itself. Could a subtle flaw in the photographic emulsion on one plate have created a false star? The answer was a firm no, because these stars appeared on multiple independent plates from different observatories, all taken before 1950. Could atmospheric turbulence have blurred the star's light on the later plates? This too was ruled out, as the disappearances were absolute and consistent across multiple new observations. The possibility of a fast-moving asteroid or a distant comet passing directly in front of the star was carefully considered. Such an event could, in theory, block the light temporarily, but the odds of a solar system object perfectly eclipsing 26 different stars and doing so permanently are astronomically low. These stars did not blink out for a single night, they were gone for good. The most compelling ordinary explanation was that the stars had not vanished, but had simply dimmed beyond the detection limit of the telescopes. Perhaps they were long-period variable stars like Vera variables that undergo dramatic changes in brightness over many months or years. Yet even the faintest, most dormant variable star leaves a faint infrared signature, a residual heat that modern telescopes should be able to detect. For these 26, the disappearance was total. There was no gradual fade, no dimming curve. It was a binary transition from visible to invisible, a light switch being flipped off. After this exhaustive process, the ordinary had been exhausted. The only possibilities left were the ones that rewrite the rules of physics. So the most dramatic and logical explanation is a stellar death, a supernova. Picture a star after millions or billions of years, finally exhausting its nuclear fuel. The outward pressure that has supported it against its own immense gravity suddenly vanishes. In a cataclysmic instant, the star collapses inward and then rebounds in an explosion of unimaginable power. For a few weeks, this single event can outshine the combined light of every other star in its host galaxy. From our distant vantage point, such an explosion would indeed look like a star flaring with incredible intensity before winking out of existence forever. It seems like a perfect answer, but the universe always leaves a mess. A supernova is not a clean deletion. It is a violent, messy divorce, scattering the star's guts across light years of space. That debris forms a beautiful, expanding cloud called a supernova remnant, like the Crab Nebula, a ghostly echo of the explosion that we can observe for thousands of years. And at the very center, the core of the star is crushed into an ultra-dense object, either a neutron star or a black hole. Both of these remnants are detectable with our modern instruments. We should see the cloud. We should detect the neutron star's lighthouse beam of radiation if it's pointed our way. For all 26 of these vanishing stars, the follow-up observations revealed a profound and unsettling nothingness. There were no glowing nebulae, there were no pulsing beacons. The space where the star once resided was empty, silent, and dark. Their disappearance was not a grand finale, but a quiet and total erasure. This pointed to a death with no aftermath, a stellar exit that defied the standard script. But if a star cannot die with a bang, perhaps it dies with a whimper. This line of reasoning led scientists to a radical and elegant alternative, the failed supernova. Imagine a star so massive that its own gravity is an overwhelming force. When it finally runs out of fuel, the core collapses under its own weight, as it always does. But in this scenario, the collapse does not trigger a rebound explosion. Instead, the core's descent into a black hole happens with such speed and finality that the rest of the star, the entire outer envelope of gas, has nothing to push against. There is no rebound, there is only the pull. Think of it not as a dynamite blast, but as a building silently vanishing into a sinkhole that opens directly beneath it. The structure is swallowed whole, leaving no rubble, no dust cloud, just an empty lot. In cosmic terms, the star is pulled directly into the black hole forming at its heart. The light from its surface would redden and dim as the intense gravity stretches the photons, pulling them back like rubber bands until they simply fade from view. From our perspective, the star would appear to wink out of existence. There is no colossal flash, no expanding nebula, and no spinning neutron star left behind. The entire event is shrouded in darkness, a silent and invisible death. This theory of direct collapse became a leading candidate because it so perfectly matched the evidence, or rather, the lack of it. It presented a mechanism for a star to be deleted from the universe, leaving behind only a heavier black hole and a profound silence. This theory of a silent, sinkhole death is compelling, but it immediately confronts a profound physical dilemma. The very process of a star collapsing directly into a black hole is not an instantaneous deletion from the outside in. It is a complex internal transformation. As the star's core gives way, a boundary of no return called the event horizon begins to form at its center. This is not a solid surface, but a point of infinite gravity from which nothing, not even light, can escape. This event horizon then rapidly expands outward, swallowing the star's layers from the inside. The star is essentially eating itself. From our distant viewpoint, the light from the star's surface would tell a strange story. The intense gravity of the newborn black hole would stretch the last photons of light, shifting them to longer, redder wavelengths before they are finally consumed. The star wouldn't just vanish, it would redden and dim in a very specific, predictable way over a period of days or weeks. This theoretical light curve is a key prediction, a ghostly signature we could potentially look for. Yet here lies the critical puzzle. Even a black hole born in silence is rarely truly dark. The violent collapse and the infall of surrounding material should create a swirling, superheated maelstrom of gas and dust around the black hole, known as an accretion disk. As this matter spirals inward at nearly the speed of light, it is heated to millions of degrees, releasing a torrent of high-energy radiation, most notably in the form of X-rays. This is not a subtle signal. Our space-based X-ray telescopes are designed to scan the heavens for exactly this kind of powerful, pinpoint emission. For a stellar mass black hole forming in our cosmic backyard, this X-ray flash should be a brilliant beacon, a definitive announcement of a birth in darkness. And this is the stubborn silence that deepens the mystery. In the precise locations of those 26 vanished stars, our most sensitive instruments have detected no such X-ray afterglow. There is no fading echo of a feast, only an ongoing, unnerving quiet. The black hole theory offers an elegant mechanism for disappearance, but it seems to predict a signal that we simply do not see. Perhaps a cosmic curtain simply closed in front of them. Before we journey to the edges of physics, we must consider a more grounded, almost mundane possibility, one that fills the vast emptiness between stars. Our galaxy is not a perfect vacuum. It is threaded with enormous, diffuse clouds of gas and minute particles of dust, collectively known as the interstellar medium. Picture a haze of fine smoke drifting through a dark forest, a haze that can subtly dim and redden the light from distant lanterns. A particularly dense, cold cloud of this material, a dark nebula, could theoretically drift directly into our line of sight with one of these stars. From our perspective, it would be as if a veil had been drawn, causing the star to fade from view not because it died, but because it was hidden. This is a perfectly normal astronomical occurrence, but it operates on a specific timescale. These interstellar clouds are immense, often light years across, and they move at a stately galactic pace. For one to cover a star would be a slow, gradual process, like a fog bank rolling in, not an instantaneous switch from light to dark. The star would dim over a period of years or decades, not between one photographic plate and the next. Furthermore, while such an event is entirely plausible for a single, unlucky star, the odds of it happening to 26 separate, unrelated stars, all within the same few decades and all resulting in a complete and permanent blackout, are vanishingly small. It would be an incredible and frankly suspicious coincidence. The pattern of disappearances points away from random external obstructions and toward something intrinsic to the stars themselves, a shared fate that struck them all from within. Another cosmic sleight of hand involves not the star itself, but the very fabric of space it travels through. Einstein's theory of relativity revealed that gravity is not just a force, but a warping of spacetime. A massive object like a star or a black hole creates a dip in this cosmic fabric. When light from a distant star passes near such a massive object, its path is bent following the curve of this gravitational well. This phenomenon is gravitational lensing. In its most dramatic form, it can act like a natural telescope, magnifying the background star's light, making it appear brighter than it truly is, or even splitting its image into multiple arcs or a perfect ring of light. This is a confirmed and powerful tool used by astronomers to study the most distant objects in the universe. But what if the reverse happened? Imagine a precise, temporary alignment. A dark, massive object, perhaps a rogue planet or a solitary black hole, drifts silently through space. For a brief period, its gravity perfectly focuses the light from a more distant, otherwise faint star, causing that star to flare up in our sky. Then the alignment shifts, the cosmic lens moves on, the magnification effect ends. From our viewpoint, the star would not explode or fade slowly. It would simply snap back to its true, dim brightness, or vanish entirely if it was too faint to see without the lensing boost. This is a compelling idea, a celestial mirage that could create the illusion of a disappearance. Yet the odds are stacked against it. For this to explain our 26 missing stars, each one would have to be the beneficiary of a separate, long-lasting lensing event that just happened to conclude sometime after 1950. The required alignments are incredibly precise and transient, lasting years at most, not the decades these stars were visibly present. A temporary lensing event ending might explain 1 or 2 odd cases, but it cannot account for a pattern of 24 permanent vanishings. The universe is a master of illusion, but this particular trick feels too fragile to explain such a definitive and repeated act of erasure. When every natural explanation seems to fall short, the mind instinctively reaches for the extraordinary. This brings us to the most sensational and imaginative hypothesis, one that steps beyond astrophysics and into the realm of pure speculation, the possibility of alien megastructures. The idea was first proposed by physicist Freeman Dyson, not as a blueprint for aliens, but as a thought experiment about the ultimate energy needs of a civilization. He reasoned that any society advancing over millions of years would eventually require energy on a scale we can barely comprehend, far beyond what a single planet can provide. The logical solution would be to dismantle planets and construct a vast swarm of orbiting collectors, a Dyson sphere that would completely encapsulate the parent star, capturing nearly 100% of its light output. From our distant viewpoint, such a star would not explode or dim. It would simply vanish, its light converted into usable energy for purposes we cannot imagine. This idea connects directly to the famous Fermi paradox, the puzzling question of where all the aliens are. If intelligent life is common, why do we see no evidence of it? One haunting answer is that advanced civilizations might be invisible by design, having transitioned to a stage where they manipulate entire stars, leaving behind only cold, dark megastructures as their signature. The search for such artifacts, known as technosignatures, is a serious, albeit fringe, branch of astronomy. The 26 vanished stars become prime candidates not for natural death, but for cosmic engineering projects of unimaginable scale. Yet for all its captivating appeal, this hypothesis stands on the very edge of science. It is a thought experiment pushed to its limit, a concept born from our desperation to explain the utterly inexplicable. There is currently no way to test for a Dyson sphere, no instrument that can distinguish its artificial silence from the natural silence of a failed supernova. It remains the explanation of last resort, a dramatic placeholder for our ignorance. Its true power is to highlight the profound depth of the mystery, revealing how far we must stretch our understanding when faced with a universe that seems to break its own rules. The search must therefore swing back from the edge of speculation, back to the realm of testable physics, where an even more fundamental puzzle awaits. The dates on those glass plates are not just timestamps, they are silent witnesses to the moment of disappearance. When astronomers plotted the vanishings against the calendar, a curious pattern began to emerge. The 26 stars did not wink out randomly over a century of observation. Instead, their disappearances were curiously clustered within a specific window of time, roughly spanning from the late 1940s to the early 1950s. This is not a random scattering. A cluster in time is a clue in itself. If these events were truly independent, driven by the internal fate of each star, we would expect them to be spread evenly across the decades. The fact that they are grouped so tightly suggests a different possibility, that a single, broader cause might have been at work. Perhaps a wave of some kind passed through our galactic neighborhood, triggering a synchronized collapse of unstable stars. Or, more troublingly, it raises the question of a systematic error. Could a flaw in the observational methods of that specific era have created the illusion of these vanishings? The astronomical community from that period relied heavily on a specific set of sky surveys, and a problem with the emulsion chemistry used on the plates, or a subtle change in telescope calibration could theoretically produce false positives that later, more advanced surveys failed to confirm. Yet this explanation also feels incomplete. The stars were recorded on multiple independent sets of plates from different observatories, all converging on the same pre-1950 presence. The clustering is real, but its meaning remains opaque. The challenge lies in the nature of the evidence itself. These are not real-time observations. The vanishings are bracketed by the dates of the last plate that saw the star and the first plate that did not. An event that happened in 1948 might not have been caught until a new survey in 1952. This fuzzy timeline makes it impossible to say if the stars disappeared in a single, dramatic night or over a period of several years. The clustering points to a shared trigger, but the historical data acts like a blurry lens, preventing us from seeing the exact sequence of events. This temporal clue deepens the mystery rather than solving it, forcing us to ask what could have happened in that specific slice of the 20th century to erase 24 stars from our view. The silent testimony of those old photographic plates demanded a verdict from modern science. Armed with telescopes of unimaginable power, astronomers have returned to the empty coordinates, searching the void with instruments that can see far beyond the limitations of glass and emulsion. The Hubble Space Telescope has peered into these patches of darkness, its digital eyes capable of detecting the faintest glimmers of ancient starlight. Next-generation observatories like the Vera Rubin Observatory are preparing to scan the entire sky with unprecedented depth, hunting for any trace of movement or change. The question is simple and profound. Have any of these 26 ghosts returned? The answer is a resounding and unsettling no. Not a single one of the vanished stars has flickered back into view. More importantly, these powerful telescopes have not found even a hint of what was left behind. There is no faint, cooling white dwarf, no telltale infrared glow of a debris field, no X-ray signature of a feeding black hole. The darkness is absolute. This modern confirmation transforms the mystery. It rules out the possibility that we were simply missing something, that the stars were merely hiding just below the detection threshold of older technology. Their disappearance was not an illusion of poor eyesight. It was a permanent deletion witnessed by both the primitive and the advanced. The phenomenon is real. The blank spaces on the map are not errors. They are questions written in the fabric of space itself, and 21st century science has just confirmed that we still cannot read the answer. The story of the 26 does not exist in a vacuum. As our technology has sharpened, so has our ability to witness these cosmic disappearances in real time, adding new and equally baffling chapters to the mystery. A particularly striking case occurred in the constellation Aquila, the Eagle, in the year 2009. Astronomers were actively monitoring a massive, luminous star, a type known as a luminous blue variable. These stars are notoriously unstable, prone to giant outbursts and dramatic changes in brightness. Then it was gone, not over centuries but within a single observing season. This was not a discovery made by comparing dusty archives, but a real-time observation of a star simply ceasing to exist. The event was captured by the powerful Large Binocular Telescope in Arizona, an instrument far more sophisticated than the photographic plates of the mid-20th century. This modern vanishing act presented a critical opportunity. Scientists immediately trained a battery of observatories on the spot, from the Hubble Space Telescope to the infrared-sensitive Spitzer Telescope and the X-ray detecting Chandra Observatory. They searched for any sign of the star's demise, a supernova's fading glow, a cloud of warm dust, or the high-energy signature of a newborn black hole. They found nothing. The silence was as profound as it was for the original 26. This modern case, and a handful of others like it, forces a crucial comparison. Are we seeing the same phenomenon play out with better cameras, or is this a different kind of stellar death? The star in Aquila was a different type of star, much larger and more unstable than the seemingly ordinary stars from the original list. This suggests that the ability to vanish may not be confined to one specific class of star, but could be a potential fate for a wider range of stellar objects. The modern cases, with their richer data and confirmed instant of disappearance, confirm that the phenomenon is real and ongoing. They transform the original 26 from a curious historical anomaly into potential evidence of a broader, recurring astrophysical process, a hidden chapter in the life cycle of stars that we are only just beginning to read. When the known laws of physics offer no satisfying answer, science must look beyond them. This is where the mystery of the vanishing stars pushes us into the realm of theoretical physics, a landscape populated by exotic particles and forces that may or may not exist. Here, the explanations become as strange as the phenomenon itself. One possibility involves the star's very composition. What if these were not ordinary stars made of protons, neutrons, and electrons? Imagine instead a star built from a hypothetical form of matter known as a cue ball, a stable, supersymmetric lump that could, in theory, be as massive as a star. A cue ball star would not shine through nuclear fusion. Its energy would come from the decay of its own exotic fields. Such an object could, under the right conditions, simply unravel or vanish in a process that emits no light, leaving behind no remnant we could detect. It would be a cosmic sleight of hand performed with a substance we have never seen. Another speculative idea involves strange matter. This is a theoretical substance composed of strange quarks, which could be more stable than ordinary atomic matter. A small seed of this strange matter, called a strangelet, could theoretically collide with a normal star. Upon contact, it might catalyze a chain reaction, converting the entire star into a lump of invisible, dense, strange matter. The star would effectively be transmuted, its light extinguished as its fundamental particles are rewritten. This would be less a death and more a metamorphosis into something dark and undetectable. Perhaps the most profound possibility connects the vanishings to the universe's greatest unsolved puzzle, dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we have no idea what it is made of. What if it isn't perfectly smooth? What if dark matter forms dense, asteroid-like clumps that drift through the galaxy? A chance collision between a star and one of these invisible, massive clumps could inject a tremendous amount of energy directly into the star's core. This sudden shock could destabilize it, triggering an immediate and total gravitational collapse without the standard supernova fireworks. The star would be snuffed out by an invisible bullet. These theories are not yet science, they are the leading edge of scientific imagination. They demonstrate how a stubborn cosmic mystery can become a powerful probe. The persistent silence where 26 stars once shone might be our first clue that the universe contains forms of matter and energy far stranger than we have ever dared to dream. This profound silence leads us to a puzzle of cosmic proportions. The mystery of the vanishing stars is not an isolated curiosity. It is deeply entangled with the single greatest enigma in modern cosmology, the problem of missing mass. For nearly a century, astronomers have known that the universe does not add up. When we observe the rotation of galaxies, we find that the visible stars and gas clouds at the outskirts are moving far too quickly. The gravity generated by all the matter we can see is simply not enough to hold these speeding stars in their orbits. It is as if you watched a child on a merry-go-round, spinning so fast that the centrifugal force should fling them off into the distance, yet they remain firmly in place. The only explanation is that there is much more mass present than we can account for, an immense, invisible gravitational anchor holding the entire structure together. This unseen substance is what we call dark matter. It makes up roughly 85% of all the matter in the universe, and we have no idea what it is. Its presence is felt only through its gravitational pull, a ghostly hand guiding the cosmos. This is where the 26 vanished stars present a tantalizing, if speculative, connection. Could their disappearances be a clue to the nature of this missing mass? Perhaps these events are not just random stellar deaths, but a process where normal, visible matter is being actively converted into something dark and undetectable. Imagine if every time a star vanished, its mass was not destroyed but transformed. The star's material could be collapsing into a form of matter that no longer interacts with light, effectively joining the vast, hidden reservoir of dark matter that permeates the galaxy. Each disappearance would then be a small, local contribution to the global dark matter budget, a single brick being added to the invisible foundation of the universe. This idea elevates the mystery from a collection of strange anecdotes to a potential window into one of physics' most fundamental questions. If true, we are not just watching stars die, we are witnessing the universe secretly balancing its books, hiding its true mass in plain sight. The empty spaces on those old photographic plates might contain the signature of a cosmic alchemy we are only beginning to comprehend. This silent transformation of matter is a ghostly process we have so far only glimpsed in hindsight. To witness it directly requires a new kind of astronomy, one that watches the sky not as a static portrait but as a living, breathing cinema. This is the emerging frontier of time-domain astronomy, a discipline built on the principle that the universe is in constant, dramatic flux. Its mission is to capture change as it happens, to turn the cosmos from a collection of frozen snapshots into a real-time movie. The challenge is immense. The sky is vast, and a star could vanish at any moment, anywhere. Catching that single, critical event demands a relentless, automated vigilance. Projects like the Zwicky Transient Facility in California are already leading this charge. Using a powerful wide-field camera, it scans the entire visible sky every 2 nights, automatically comparing each new image to the last. It flags anything that has changed, from exploding stars to moving asteroids, generating thousands of alerts for astronomers to investigate. This is a fire hose of data, a systematic search for the extraordinary hidden within the routine. But this is only a preview of what is to come. The future of this hunt rests with the Vera Sea. Rubin Observatory, currently under construction in Chile. When it becomes operational, its massive mirror and enormous digital camera will photograph the entire visible sky every few nights with breathtaking sensitivity. Over a decade, it will create the deepest, most comprehensive movie of the universe ever made, a time-lapse of the cosmos on a scale that was once unimaginable. It is our best hope for finally catching a star in the very act of disappearing. The critical evidence will be written in the star's final moments, in the precise shape of its light curve. A gradual dimming and reddening over days or weeks would be the ghostly signature of a star collapsing directly into a black hole, its light stretched and smothered by intense gravity. An instantaneous cutoff, a light that snaps off like a switched-off bulb, would be far more shocking. Such a clean break is difficult for any known natural process to explain and would force us to consider even more exotic possibilities. Each flicker, each subtle change in brightness, is a data point that could rule out entire classes of theories. The dream is to have multiple telescopes, sensitive to different wavelengths of light, all swing into action the moment an alert is sounded. We would see the event not just in visible light, but in the infrared, in ultraviolet, in X-rays. That multi-wavelength portrait would be the ultimate clue, revealing the true mechanics of the vanishings. The solution to this decades-old mystery may not come from reanalyzing old glass plates, but from a new alert on a computer screen, a single data point signaling that somewhere in the darkness, a light is going out for good. The profound unease we feel when a star vanishes is more than just scientific curiosity. It is a deeply human reaction. For all of recorded history, the stars have been our constants, the unwavering guides in a world of change. Ancient navigators used them to cross trackless oceans, civilizations built their mythologies around their patterns, and philosophers saw in their perfect regularity a model for cosmic order. The idea that these eternal lights can be snuffed out and erased so completely strikes at the very foundation of that security. It tells us that the cosmos is not a static backdrop but a dynamic and potentially unstable arena. This mystery resonates because it challenges our most basic assumption that the universe is predictable and knowable. It forces us to confront the possibility of forces and processes operating on a scale and in a manner we do not yet understand. Unlike other great puzzles, such as the nature of dark energy or the origin of the universe, the missing stars are a tangible absence. We can point to a specific spot in the sky and say, something was there, and now it is not. That concrete void is a powerful hook for the imagination. This public fascination is not a passive distraction. It is the engine that drives fundamental science forward. The desire to solve such a captivating puzzle builds support for ambitious projects like the Vera Rubin Observatory, translating wonder into the concrete funding needed to build the tools of discovery. In the end, the search for these 26 ghosts is a testament to an insatiable human need, not just to catalog the heavens, but to truly comprehend our place within them, even when the universe seems determined to hide its deepest secrets. The silent erasure of a star is a whisper of a far greater cosmic truth, that permanence itself may be the ultimate illusion. We are forced to confront the ephemeral nature of all existence, from the briefest human life to the billion-year lifespan of a sun. Our entire civilization is built upon the assumption of stable foundations, but the universe operates on a scale where even the grandest structures are temporary arrangements of energy. A star that simply vanishes asks a deeply unsettling question. If something so massive and enduring can be deleted so cleanly, what guarantees do we have for anything at all? This mystery pulls the rug out from under our feet, revealing a cosmos not of fixed clockwork but of constant dynamic flux. The contrast in timescales is almost incomprehensible. A human life is a flicker, a single frame in a movie that lasts for billions of years. A star, by comparison, seems like the theater itself, a permanent stage upon which our brief drama plays out. To learn that the stage itself can be dismantled in an instant redefines our understanding of legacy. What does it mean to leave a mark when even the mightiest celestial bodies can leave none? This is not a call for nihilism, but for a profound shift in perspective. It suggests that meaning is not found in everlasting monuments, but in the dynamic processes of change and transformation that shape the cosmos. The search for these vanished stars is more than a scientific puzzle. It is a philosophical quest. The answers we eventually uncover will not just fill in blank spaces on a star chart. They will force us to reimagine our relationship with the universe. We may discover that we live in a reality far more mysterious and interconnected than we ever believed, where disappearance is not an end, but a transition into a state we have yet to comprehend. To understand this cosmic riddle, we must examine a single case in precise detail. Among the 26, one star stands out for the clarity of its record and the finality of its departure. Its official designation is TYC 41224261, a string of numbers that belies its profound mystery. This star was located in the northern constellation of Lyra, the Harp, not far from the brilliant Vega. On photographic plates exposed between the years 1900 and 1949, it appeared as a steady, unremarkable point of light with a magnitude of approximately 13.5. To the unaided eye, this is utterly invisible, but for the telescopes of the era, it was a clear and consistent presence. Its spectrum, the chemical fingerprint of its light, suggested it was an ordinary main sequence star, similar to our own sun but much farther away, quietly burning its hydrogen fuel. There was nothing in its recorded behavior to suggest it was unstable or nearing the end of its life. It was, by all accounts, a perfectly normal citizen of the galaxy. Its story is written on two specific sets of glass plates. The first is from the Henry Draper Memorial Sky Survey, a pioneering project that meticulously catalogued the heavens in the early 20th century. On plates taken in 1900 and 1911, the star is unequivocally there. The second critical record comes from the National Geographic Society Palomar Observatory Sky Survey, the POS, one of the most comprehensive astronomical archives ever created. Its first epoch of observations, conducted in the late 1940s, also clearly captured the star. But when the same region was photographed again for the second POS epoch in the early 1990s, TYC 41224261 was gone. The time window for its disappearance is therefore pinned with remarkable precision. It was present in 1949. It was absent by 1951. Sometime within that two-year span, this star, located thousands of light-years away, ceased to exist in our sky. This is not a blurry historical account. It is a stark before and after snapshot. The meticulous cross-checking of these independent surveys eliminates any possibility of a plate defect or cataloging error. For this one star in this one patch of sky, the universe performed a perfect magic trick, leaving behind not even a wisp of cosmic dust as a clue. Yet another star tells a different story, deepening the pattern of inconsistency. While the star in Lyra was a quiet sun-like object, a second case from the constellation of Gemini presents a stark contrast. This star, catalogued as TYC 1860001, was nearly 5 times brighter than its counterpart, a significant difference that made it a prominent feature on the photographic plates. More intriguing than its luminosity, however, is its timeline. The evidence suggests this star vanished not in the clustered window of the late 1940s, but significantly later, sometime between the early 1950s and the mid-1960s. This temporal shift is crucial as it challenges the idea of a single, synchronized event passing through our galactic neighborhood. Here we have two stars, one dim and one bright, disappearing at distinctly separate moments in history. The differences between them seem to argue against a one-size-fits-all explanation. A star's brightness is directly tied to its mass. A brighter star like the one in Gemini is inherently more massive, and a more massive star lives a much shorter, more violent life. It burns through its nuclear fuel at a ferocious rate, destined for a cataclysmic end as a supernova. The dimmer star in Lyra, by comparison, was a placid, long-lived dwarf. If their disappearances were due to their internal clocks running out, we would expect them to die in completely different ways, on vastly different timelines. The massive star should have died in a spectacular explosion, while the smaller one should have faded slowly into a white dwarf. The fact that both simply vanished, leaving the same profound silence, is the central paradox. Their shared fate, despite their different natures, points away from individual life cycles and toward an external trigger, a mechanism that can strike any star, regardless of its mass or age. This comparative analysis forces a difficult choice. Either we are looking at two different vanishing mechanisms, one for massive stars and one for small, which seems an unlikely coincidence, or we are witnessing a single, universal process that overrides a star's intrinsic properties. The empty spaces in the sky are not just absences, they are comparative data points. By holding them side by side, we see that the mystery is not merely about stars disappearing, but about a phenomenon powerful enough to erase the very distinctions between them. This collaborative search for answers is no longer confined to professional observatories. The sheer volume of data generated by modern sky surveys is so immense that no single team of astronomers could possibly analyze it all. This is where the power of the crowd enters the story, transforming every curious individual with an internet connection into a potential cosmic detective. Online platforms like Zooniverse host citizen science projects that invite the public to sift through the same astronomical data used by professionals. You might be looking at images from the Hubble Space Telescope or the latest scans from a survey like the Zwicky Transient Facility. The task is often to look for the unusual, a subtle change or an odd shape that a computer algorithm might have missed. Why are human eyes so valuable in an age of artificial intelligence? Because our brains are exquisitely tuned for pattern recognition. We are naturally gifted at spotting anomalies, the one thing that looks out of place in a field of thousands. An algorithm is trained to find what it already knows, but a human observer can stumble upon something truly strange, something that defies all existing categories. This is how a teacher, a student, or a retiree sitting at their kitchen table could be the first to notice a star that is no longer where it should be. The search for these vanishing acts has become a truly democratic endeavor. It means the next critical clue, the one that cracks this mystery wide open, might not come from a PhD in astrophysics, but from an amateur enthusiast who simply noticed that a single point of light had gone dark. This collective effort reminds us that the universe belongs to everyone, and its greatest secrets are waiting for any pair of eyes willing to look. The allure of a cloaked alien mothership or a glitch in the cosmic code is undeniably powerful. When faced with a mystery as profound as a vanishing star, our minds naturally leap to the most spectacular possibilities. Yet the true path to an answer requires us to walk past these tantalizing fictions and stick to the harder road of evidence. The idea that these stars are actually alien megastructures, like Dyson spheres, is a hypothesis born from a logical, if extreme, extension of known physics. But the suggestion that they are literal spaceships using some form of cloaking device steps firmly into the realm of science fiction. For such a vessel to mimic a star perfectly for decades and then vanish, it would need to not only generate the exact light signature of a sun, but also perfectly simulate its gravitational pull and heat signature across all wavelengths. The energy required for such a perfect, sustained illusion, and then for the ship to accelerate away at speeds that leave no trace, defies any known principle of conservation of energy. It creates more physical problems than it solves. Similarly, the notion of a dimensional portal or a rip in space-time is an appealing metaphor, but it lacks any mathematical foundation in our current understanding of relativity. Such an event would be anything but quiet. The violent warping of space-time required would unleash gravitational waves of unimaginable strength, ripples in the fabric of the universe that our detectors like LIGO and Virgo would have sensed from across the galaxy. The silence surrounding these vanishings is, in fact, the strongest evidence against these sensational ideas. They are not accompanied by the energetic fireworks that such monumental events would inevitably produce. Even the simulation hypothesis, the idea that our reality is a construct and these vanishings are errors or patches, is ultimately a philosophical dead end. It offers no testable predictions. If we accept that the rules of physics can be arbitrarily broken, then the entire scientific endeavor, the search for consistent laws that govern the cosmos, becomes meaningless. We are left with no way to distinguish between a real phenomenon and a programmer's whim. This is not to stifle imagination, but to channel it productively. The human desire for awe is what drives us to look up in the first place, but that same wonder must be coupled with disciplined skepticism. By systematically eliminating the impossible, no matter how exciting it might be, we clear the ground for the truly extraordinary reality that might be waiting, a reality that could be far stranger than any fiction. The silent perfection of these vanishings points toward a pattern, but one too subtle for any human eye to discern. Cracking this code demands a new kind of detective, one that can process the entire night sky not as a collection of images, but as a river of flowing data. This is where the centuries-old discipline of astrophysics converges with the revolutionary power of modern data science. The hunt for vanishing stars is no longer just about building bigger telescopes, it is about writing smarter algorithms. Imagine the sheer volume of information involved. A single night of observation with an instrument like the Vera Rubin Observatory will generate over 20 terabytes of data, the equivalent of streaming high-definition video for over a year every single night. Within this tsunami of numbers, the signal of a star disappearing is an infinitesimally small ripple. Finding it manually would be like searching for one specific grain of sand on every beach on Earth. This is where machine learning enters the story. Scientists are now training artificial intelligence systems on the known cases, teaching them the digital signature of a star that is present and then absent. But the real power lies in going beyond mere imitation. These algorithms can be set loose on vast archives of historical data, from those old photographic plates to modern digital sky surveys, and instructed to look for anything that behaves unusually. They are not just matching a pattern, they are searching for anomalies, for outliers that defy every known classification of variable star, asteroid, or instrumental error. They can detect a subtle, gradual dimming that precedes a disappearance, a faint reddening of light, or a statistical clustering of events in time and space that would be invisible to us. This synergy is transforming the mystery from a collection of cold cases into an active, data-driven investigation. The solution may not be locked in a distant nebula, but buried in plain sight within petabytes of information, waiting for the right line of code to connect the dots and reveal the hidden law behind the silence. The ultimate arbiter in this cosmic court will be a new generation of eyes, tuned to see what previous telescopes could not. The James Webb Space Telescope, orbiting 1 million miles from Earth, represents a fundamental shift in our perception. Its primary mission is to see in infrared light, the domain of heat, while an optical telescope like Hubble sees the visible light that has gone missing. James Webb is designed to detect the faint, residual warmth of cold objects. It can stare into the precise coordinates of a vanished star and search for the ghostly infrared glow of a cold, dark remnant. If the star collapsed into a black hole that is now drifting silently, it would be invisible. But if it left behind a cooling white dwarf or a neutron star that has fallen dormant, James Webb might detect its faint heat signature, a dying ember against the blackness of space. This would solve the mystery for good, confirming a natural, if quiet, stellar death. But if even James Webb sees nothing but profound cold, the case for something truly exotic grows stronger. Beyond light, we are learning to listen to the universe. Gravitational wave observatories like LIGO and Virgo have opened an entirely new sense, allowing us to feel the ripples in spacetime itself. These instruments have already detected the collisions of black holes and neutron stars, cosmic events that shake the very fabric of reality. A star collapsing directly into a black hole would be a quieter event than a collision, but it would still generate a unique gravitational wave signature, a brief, low-frequency shudder as the star's mass vanishes behind an event horizon. Future, more sensitive space-based detectors, like the proposed Laser Interferometer Space Antenna, or LISA, will be tuned to listen for these specific frequencies. They could, in theory, hear the silent scream of a star being swallowed by its own gravity, providing a confirmation that light-based telescopes never could. The tools to solve this mystery are not just being built, they are already pointing at the sky. The next decade will not be one of passive observation, but of active interrogation, as we question the darkness with every tool at our disposal, demanding that it finally give up its secret. So where does this leave us after sifting through a century of evidence from dusty plates to space-age telescopes? We are left not with a single, tidy answer, but with a web of compelling possibilities, each supported by clues yet burdened by contradictions. The theory of the failed supernova, the silent sinkhole collapse into a black hole, remains the most elegant natural explanation, yet it is haunted by the absence of the X-ray flash such a birth should produce. The connection to dark matter is profoundly alluring, suggesting we are witnessing the universe's hidden accounting, but it remains a speculative leap without direct proof. The historical clustering of the vanishings hints at a shared cause, while the differing nature of the stars themselves argues against a one-size-fits-all fate. This is not a sign of failure, but of a mystery being refined. Each dead end and unanswered question has systematically narrowed the field, forcing us to discard the impossible and sharpen the probable. The enigma of the 26 vanishing stars, therefore, stands as a monument to the scientific process itself. It is a powerful reminder that our maps of the cosmos are still dotted with regions marked "Here be dragons." This puzzle challenges our deepest assumptions about stellar life cycles, the stability of matter, and the very predictability of the universe. It confirms that the heavens are not a placid museum, but a dynamic and sometimes violent arena where change can be instantaneous and absolute. The enduring power of this mystery is that it refuses to be solved with the tools we currently possess, pointing insistently toward a horizon of discovery where new eyes and new senses will finally reveal what has been hiding in the darkness all along. A single anomaly on a glass plate has spiraled into one of astronomy's deepest puzzles. We have journeyed from the rhythmic click of a blink comparator to the silent interrogation of space telescopes, confirming a reality that defies easy explanation. Stars do not merely fade, they can be erased, leaving behind a void that challenges the fundamental laws we thought governed stellar life and death. Conventional wisdom, from supernovas to interstellar dust, has fallen short before this absolute silence. In its place, we are left with the thrilling, if unproven, possibilities of failed supernovas, exotic matter, and a hidden connection to the dark cosmos itself. This is the true nature of scientific discovery, a process that often begins not with a grand theory, but with a stubborn, inconvenient fact that refuses to fit. It is the anomaly that forces us to look deeper, to question our assumptions, and to expand the boundaries of the possible. The next time you gaze at the night sky, see it not as a static painting but as a dynamic, living tapestry, one where the lights we take for granted might not be as permanent as they seem. The case of the 26 vanishing stars remains open, a silent invitation for the next curious mind to pick up the trail. The universe is still writing this story, and the next chapter promises to be the most revealing.